This logic board is smaller than an iPhone. It powers an entire MacBook Air. A few years earlier, the board inside the same machine spread across most of the chassis, covered in discrete chips, voltage regulators, and memory slots. When Apple Silicon replaced Intel, it didn't just swap processors, it shrank every Mac logic board forever. And to understand how, you need to see what it replaced. Under the hood of a 2018 Intel MacBook, the Silicon layout looks like a miniature city divided into specialized districts. The Central Processing Unit, or CPU, which acts as the main brain for running applications, occupies its own massive, dedicated footprint near the center of the board. But it cannot run the machine alone. To communicate with the outside world, it relies on a physically separate chip called the Platform Controller Hub, or PCH, which manages basic input and output duties like USB ports and system audio. On high-end professional models, a discrete graphics processor, or GPU, sits in its own zone, surrounded by dedicated video memory chips and massive voltage regulator modules. Storage drives, wireless cards, and removable RAM slots spread out even further, each requiring its own supporting components and high-speed data highways etched into the fiberglass. This separation of powers forced the motherboards to sprawl across the entire chassis. This fragmented layout turned a logical circuit diagram into a severe mechanical bottleneck. Because system memory lived in physical, removable DIMM slots, the motherboard had to accommodate the thick plastic sockets and their high-speed copper traces. Every gigabyte of memory required hundreds of parallel data lines etched across the fiberglass, consuming vast amounts of surface area to prevent signal interference. Nearby, the processor's massive power demands required clustered voltage regulator modules, each with its own heat-generating inductors and capacitors. While this modular approach allowed technicians to swap individual memory sticks or repair isolated power phases, it was expensive in terms of physical volume. The sheer surface area required to host these separate subsystems meant the logic board dictated the minimum length, width, and height of the entire computer. The aluminum enclosure could only be as thin and compact as the green fiberglass board inside it, locking Apple's hardware team into a rigid, volumetric envelope. The transition away from Intel was not a simple swap of one processor for another. It was a complete architectural rewrite. Instead of a motherboard populated by isolated, specialized components, Apple's hardware engineering teams designed a single, unified system on a chip. This single package consolidated the central processing unit, the graphics processor, the 16-core neural engine, and the image signal processor onto one piece of silicon. It also subsumed the security enclave and the memory controller. Functions that previously required distinct, physically distant chips spread across centimeters of fiberglass were now packed into a tightly integrated footprint. John Ternus, Apple's Senior Vice President of Hardware Engineering, framed this structural consolidation not merely as a processor upgrade, but as an opportunity to redesign the Mac from the silicon up. By placing these core systems on a single package, the engineering teams removed the traditional physical boundaries of the motherboard. Nowhere is this more apparent than in the memory architecture. Instead of routing signals to distant memory slots, the memory controller was integrated directly onto the die, with separate LPDDR4X memory packages sitting right next to the processor on the substrate. This tight coupling eliminated the need for complex, multi-layered trace routing across the board. The processor and the memory now operated as a single unit, initiating a cascade of physical space savings across the entire machine. Unified memory means all processing blocks, the CPU, the graphics cores, and the neural engine, access a single, shared pool of memory. They no longer require separate, dedicated memory pools with their own duplicate data paths. In the first generation M1 chip, this memory takes the form of LPDDR4X SDRAM. Instead of placing these LPDDR4X chips in distant sockets or soldering them to separate sectors of the logic board, Apple mounted the memory packages directly onto the substrate of the system on a chip, immediately adjacent to the silicon die. This physical proximity fundamentally rewrote the motherboard's layout. A typical Intel-era board required hundreds of long, high-speed copper traces etched into multiple layers of the fiberglass to connect the CPU socket to the RAM slots. These traces had to be carefully spaced and matched in length to prevent signal timing errors. By placing the LPDDR4X packages directly on the processor substrate, those long DDR routing paths were entirely eliminated. The distance data travels between the memory and the compute cores shrank from several centimeters to a few millimeters. This change reduced signal interference, allowed for a simpler power delivery network, and stripped away a massive layer of routing complexity, allowing the motherboard to contract around the central package. Physical disassembly of the first M1 machines shows the scale of this spatial reduction. In the M1 MacBook Air, removing the Intel platform controller hub, discrete memory modules and complex power phases allowed the printed circuit board to shrink to an estimated 106 square centimeters. This represents an 8% reduction in surface area compared to the 2020 Intel model, even with the processor's massive 120 square millimeter die footprint. The desktop line shows even more aggressive miniaturization. Teardowns of the M1 Mac Mini show a board that leaves the vast majority of its aluminum housing completely empty. On the M1 iMac, the entire computer fits onto a narrow, elongated strip of fiberglass at the bottom of the display. In its most extreme form, this design consolidation means the entire logic board of the M1 MacBook Air is physically smaller than the outline of an iPhone. That physical shrinkage transformed the internal architecture of the entire computer. When the logic board occupies a fraction of its former footprint, the remaining internal volume becomes prime real estate for other vital subsystems. Inside portable models, this newly reclaimed space went directly to larger, thicker battery packs, providing the physical capacity needed for extended runtimes. Thermal systems could expand or be completely reshaped inside the aluminum enclosure, allowing some machines to discard the active cooling fan entirely. Shorter electrical paths between unified memory and the silicon compute cores reduced heat generation directly at the source, while having far fewer discrete components improved power efficiency and simplified the board's overall routing layout. Ultimately, this space-saving design redefined how energy and heat move through the chassis, allowing engineers to build thinner devices without compromising structural integrity or sustained performance. The MacBook Air adopted the new layout to go entirely fanless, assigning the reclaimed internal volume to a larger battery envelope for extended runtimes. The 13-inch MacBook Pro retained active cooling but reorganized its internal footprint around the compact M-series board. For desktops, the Mac Mini kept its legacy square aluminum housing while using the tiny board to alter internal component placement, leaving the chassis mostly empty. The 24-inch iMac relied on a narrow, strip-like board at the bottom of the display to achieve its thin, flat enclosure geometry. At the high end, the Mac Studio scaled this architecture upward, using a massive dual-die package to consolidate workstation-level performance on a single board, proving that the silicon-first philosophy could adapt to any form factor. Today, the boundary between silicon and chassis has dissolved. As computing power condenses, we are redefining what a computer can physically be. The ultimate form of personal hardware is still being written. What redesign do you want to see next? Share your thoughts below.